When George asked me to kind of like speak on sensor fusion, I kind of was a bit confused in this whole context, because that's a topic that's been around a long time, and obviously the question is, what do you really mean? If we go out there, there's a lot of different concepts. And so I asked George to specify, and he came back with this. He says, as you know, sensor fusion is very interesting, and the Kalman filtering is very important. So he really wanted to know why this VK error here is not related to the rest. So I'll spend the next 20 minutes talking about it. I think that's what Ernest is going to talk about. I will not. I'll try to keep it a bit simple. And I think we've heard this morning in the first session quite a few visions of where we go with mobile technology and so forth. And it's sometimes difficult, because in the daily business, when you're out there in the airborne business, you're still trying to do the kind of like the basic stuff. You're going back to reliability, you're going back to performance, you're going back to calibrations and issues that kind of like keep us bogged down every day, whilst we like to think more mobile and more real-time and more onboard processing, which we hear a little bit later on as well. So I try to reflect a little bit where we are today, which is kind of like trying to keep our feet on the ground, and then I go a little bit into data fusion, which is what we call the dynamic GIS. And the difference really here is to get real-time updates over time. And there is a lot of technologies that we need in order to get there. So whilst the vision of having a mobile cell phone in a room taking pictures and transmitting that somewhere else relatively quickly is a nice one, I think there's lots of hurdles that we still have to overcome to make that really work. But to start, I think for those of you who are young, you probably have seen these things. I spoke about UAVs last year. And I think this is one of the fascinating ways of integrating sensors. You've got tons of sensors in these little devices. And for those of you who've played with this AR Parrot that you can buy for $250 off the shelf, you load your application on your iPad or iPhone, and you start controlling that thing. No manual rhythm. It's very simple. Wireline connection, VLAN connection. You press start, the thing takes off, and you can fly it around. It's great. And I mean, obviously, for those of you who kind of been RC flyers for many, many years and try to fly helicopters, it takes years of training, hours of trying to get this thing in. But the integration of MEMS IMUs and smaller sensors in the UAV, combined with the stuff that we've got in these cell phones and mobile devices, I think makes life easy. You can do that within 5 minutes. And even my daughter, who's not even 5 years old, flies around with that thing in the house and bashes every once in a while into the floor, but it actually is quite easy. So here, I think, a very modern example of what sensor fusion can be and what it actually can, how easy it can make life. But I'm not going to talk about that because we're not selling so many of those systems, and I think for mass production or mapping applications, we're still a little bit away with these kind of things. Of course, in indoor, they're coming. One thing that we are standardly using today is, of course, GNS and IMU processing. Kalman filtering and so forth are standard processes in any of our devices, and even going further, every sensor today is almost every sensor is equipped with an IMU. It was interesting, 5 years ago, we still had debates that somebody would say a push broom sensor needs an IMU and a frame camera doesn't. Today, we deliver 95% of our cameras with an IMU, standard. Everybody uses it, it's become a standard processing tool, and of course, it's the simplest way of kind of like fusing a sensor with another sensor. I think we're even moving towards common platforms. So GNSS IMU port stacks are no longer external devices. You don't need to have an external box for GNSS IMU. It's part of your control unit. It's integrated, part of the OEM. We don't even give customers a choice. And quite frankly, they don't ask anymore. They take it, it costs you a couple of $1,000 and it's there. With the MEMS IMU, even a simple MEMS IMU you can buy for €1,000. Why waste too much time in not having it? So I think there's a lot of things that over the past couple of years have come standard. Obviously, classic one, the mounts. We still get sometimes requests whether you can actually do manual drift corrections on the mount. We're still doing manual drift corrections today. It's fully integrated. The mount, IMU, sensor, full control with the system. Whether you add a camera here, of course the design of the PAV we can discuss a lot, but I think the important part here is, and that's the software. It goes back to the software. Everything, if you want to include, or if you want to fuse sensors, the important part is that the operator can operate the sensor out of the same environment. Same one GUI, one operator interface, and you connect everything. You can switch and toggle, you can do one flight plan and so forth. All of that's standard today. There's nothing new about that. We can argue it every once in a while. This still comes to me and says, hey, when are you building a sensor that kind of like merges a LiDAR system with an imager? It's very simple to do. but it's a little bit like your home system. If your home system, your DVD and everything else is done, you're up without anything. If you have something like this that's maybe not under one hood, if the camera goes, if the LiDAR goes, you can still fly with the remaining components. The key element is that via the software everything is integrated. Again, this is standard today. But one example where you kind of like merge, and maybe this is a bit far-fetched, but then again I think it's not, because we thought about 2.5 years that's a relatively easy feat to bring in medium format market the RGB sensors with the full-scale infrared sensors to create what we call a multispectral sensor. And this is also sensor fusion, because in most cases previously with our RCD105s we had to have two camera heads, different filter on top. Problem downstream, you don't have co-registered images. You have an RGB image, you have a full-scale infrared image, but you can't bring the two together because of course your projection centers are slightly different. So with the RCD30 we brought that together, and the interesting part here is that everything downstream changes. The moment you pack these two things together, and I'll speak about that a little bit, and you can see here this is an inside view, so we have two CCDs in there with a beam splitter. It separates the two. Relatively, it looks very easy, but it's relatively complicated. But the reality is that now your downstream calibration changes. You've got to co-register those images. And that's actually one of the examples. You see it on the top line, you see if it's non-calibrated. On the bottom line, you see if those are calibrated. Because what you want to create is multispectral images that you can play around with, that are actually a 4-band, even true 4-band images, and not 3-band images, or two sets of 3-band images. I think going downstream, we now have to do a whole range of different calibrations in this. We've got to bring these bands together, we correct them step by step, and then we co-register them. Even fact, we go back and our whole calibration lab has changed. We've developed a complete new goniometer that automatically calibrates this kind of camera. Simple step, you bring RGB and false color and infrared together. The one thing is to create the development, the other thing is that your whole processing chain, from calibration right down to manufacturing, changes. That's why it's not so easy to bring sensors together. That's why it's not so easy to kind of like take a camera and a LiDAR and put it under one hood and make it all work from one scene. That's why sometimes it's easier to plug and play and bring that together in the software, and it gets much more efficiencies out of there. I think that one important thing of all the things that we see today is that what you want to do is absolutely left to your own devices. It's the use case. There's lots of information that you can get, but you've got to bring this information together. You can record a lot of things during flight. If you don't have tools to bring these things together, what use is it going downstream? And I think you've got to think of that beforehand. One of the things that we hear a lot is, of course, 3D city modeling. And so if that's a use case going forward, and you think you'd like to have oblique images and LiDAR images, you'd like to get through the trees, maybe one of the things, and that's a concept study that you were working on, is to combine a LiDAR with an imager. In this case, it's two different technologies. It's an oblique camera. You don't need the nadir view. You can replace that with a relatively narrow field of view for a LiDAR. And you have one system that fits in one camera hole. Oblique data is mostly flown with small aircraft, Cessna 206 or so forth, so you don't have the chance to have a two-hole system. Maybe that's one way. But again, I think the important part that you need to have a use case. A manufacturer like us, we cannot sit time and kind of like prototype every single system. You've got to have something that you can actually serialize and that you can bring to the market at an affordable price. So if 3D mapping is one of those things, maybe that's a use case that kind of like goes forward. I think the second challenge when we're moving on to data fusion and processing, and you all, I think, have had that challenge, is there are so many standards out there to create data sets together to kind of like join them meaningfully. And I'm not just talking about GIS, putting one GIS on top of another, one layer on top of another. I'm talking about really using the data to produce better results. For instance, using a digital elevation model to create better orthophotos and stuff like that. I think you have to have standards, and we all know that standards and achieving standards is not so easy. In 3D urban modeling, CDGML seems to be the one standard that goes like in Europe, but still, there's still discussions on the definition of level of detail 1, 2, and 3. So it's very, very difficult to kind of like bring these things together, and those are the things that we still got to overcome if we want to get to those visions that we've seen. In post-processing, for instance, one of the things that we've done in the past 2 years is, or past 3 years, is in theory to create an orthophoto. You have a whole range of data sets, and you kind of like bring these data sets. You process each data set individually, then you bring it into your software, and by the time you have them all together, you kind of like load all of those files, and then you create the ortho. The important part here is that what you want to do is you want to be able to, before you start this process, see what the result is. So you need to be able to process these things on the fly onto the screen. And thankfully, the graphic cards developments over the past couple of years, GPU processing, helps you with doing that. And so one thing that we are now doing, this fly means on the fly. For those of you who kind of like, you get various data sets, and without pre-processing, we don't process the GNSI-mu data straight away. We actually have that as raw data set, but we access it in the visualization. We access the DEM in the visualization, and we bring all those parts onto the screen so that the end operator can see what the final results will be. And then he takes all of these things, what he's made all the decisions, and pushes it once through the pipeline, and the result is hopefully exactly what he wants to do. So that's the desktop processing part, and with that we don't have to go through all these individual steps. We can go to rapid ortho processing, and I think Ernest is going to speak about that, to take that to one level further, and that's real-time processing on board, which I think is certainly something that's going to come. At the same time, we've made all these advances in creating from imagery different data sets, and that's an interesting one too, because now we can create point clouds, of course, from LiDAR. We create them from images as well. Here is an example where we, in one process, create a product that doesn't only give you the point cloud here at the bottom. We actually have the digital elevation model on the left-hand side, and we've got a classified point cloud on the right-hand side that separates vegetation from buildings, all done in one step, all done from imaging. Now, of course, you want to bring that together with LiDAR image data. First challenge is, which point do you choose? Which point do you select? And that's becoming very, very difficult. So we've done one of the examples here with the Swiss university, and that's bringing together terrestrial data, mobile data from a mobile vision system with the RCD30 airborne data. We've created point clouds. What do you think the first hurdle we came across was? The data sets didn't match by 2 meters. Why? Different coordinate systems, post-processing, and you all know how that then goes, and it takes hours and weeks in order to match that and bring them together. And of course, if you have those two data sets and let's say a street sign is 2 meters offset in one data set from the other, then how do you make the right decision? Which one do you choose? So I think there are a lot of practical problems that we got to start overcoming and solving in the way of getting all these data sets together. I think ultimately